All right. Everybody's favorite subject. Yes, we are starting. Normalization of database tables. Kind of controversial. Well, not really. There's actually really only a couple of different definitions about what's meant to have normalized tables, but I figure this is a good topic to discuss after we've already talked about SQL, and we've already talked about entity relationship diagramming and designing good tables. And I guess the biggest question that a lot of people have to ask themselves is, what does it mean to actually have a good design? And do you really want first, second, third, or fourth, or fifth, or sixth normal form, and what difference does it make? And in some cases, actually, you might be surprised to find out that fourth normal form may not necessarily be better than third normal form. It depends on what you're trying to strive for. The more perfection you put in the database design, the higher the normal form, usually the harder the database is to work with, the harder it is to get information into the database. So there's a fine line in the design that you kind of meet. It's usually around third normal form, where you stop trying to optimize it and you work with well enough is enough. You leave well enough alone. You get to there. So what am I talking about? Don't worry about it if you don't know what these normal forms are yet. I'm going to explain everything. So what normalization is, the role it plays with the database design process, we're going to look at. About the normal forms, first, second, third, BCNF, I'll talk about that, how normal forms can be transformed from lower to higher normal forms, and normalization and ER modeling. We're not going to go through the ER process, but we'll talk about the modeling concept of the entities and the relationships and how that creates normal forms concurrently to produce a good database design. And it looks at some situations that require denormalization to generate information efficiency. So we're going to take something out of fifth and put it into fourth or third to denormalize something, which is something you actually kind of have to think about in terms of why is it needed. Sometimes it is in order to make the database more efficient, to make it more flexible, to make it workable. So normalization by definition is the process for evaluating and correcting table structures to minimize data redundancies and help eliminate data anomalies. So one of the biggest concerns about databases is being able to get at the information. So we take a bunch of data, we break it out into objects or entities, we look at the relationships, we turn those into tables, and then we want to put it all back together. Which just seems kind of contradictory in theory, because the storage that we're trying to achieve is very specific, because every table is supposed to have only the data that's necessary for that particular entity. So it's kind of, it's kind of like working backwards to take all of those and put them all back together again, which is essentially the concept of using SQL on the tables. So in terms of working through, we go through a series of stages. So what I'm going to do is show you a no normalization. Put that into a normal form, a first normal form. We'll take a look and we'll see what that looks like. And then we'll look at second normal, then we'll look at third normal. And then I'm not going to take it past third normal form, because if you can get something in third normal form, you're okay. You're average. Actually, you're good. You're better than average. Most databases are somewhere between 2 and 3 normal form. The fourth and the fifth normal form databases, hard to work with. Hard to work with. Not necessarily something you want to strive for. Because a lot of students ask, well, how come just third normal? Actually, you can get even higher than fifth and sixth. You can get way high on the normal forms. Why? I have no idea. Why do you want to? But all right, so second normal form is better than first. Third is better than second. The higher the number, theoretically, the better. The consistency, lack of redundancy, all those certain things. And I'll talk about what it means to be in each one of them, and that make more sense to you. For most database designs, the third is the highest that you need to go into. Higher levels, normality is not always the most desirable, as I mentioned before. Okay, so let's say we have an example company that manages building projects. And what I want to do is kind of take the process of what normally happens. If you're following an entity relationship diagramming model, you're creating third normal form databases out of that. That's why people go with that standard. And they use that methodology because it guarantees unless you don't use the model correctly, you're going to have third normal form database tables. not everybody uses that methodology. Some people actually take spreadsheets and they turn them into databases, or they use their own hacked way of designing the database structure. So what we're going to look at is a sample company that's got a spreadsheet, and a spreadsheet has manages building projects, and we've got it charges its clients by building hours spent on each one of the contracts. Hourly billing rate is dependent on the employee's position. And periodically a report is generated that contains information that's going to be displayed in this next figure 5.1. Don't worry if you can't see this. Actually, here, I'll zoom in on it momentarily so you can kind of get a feel for what this looks like. It's kind of a report. So what we are going to do, don't do at home. This is bad database design. We're going to take and purposely create a bad design because we need to show you what's the difference between first, second, third. Because most of you, why would I want to? No. See, you all know about databases. You already know about entity relationship diagramming and stuff like that. This is designed for people who are going to take the wrong steps. They're going to take this report and they're going to turn it into a database. Because that's what people do, actually. So we got a table. We've got the project number, name, employee. We don't have to look at all this stuff, but that's a sample report that's coming out of the system of a current program that they have. So now they take it. And this is why people like Microsoft Access. They can actually pretty much dump the information out and import it into Access. Looks like a spreadsheet, but it's in a database. And then they call it a database, and they think they've actually created a database out of it. What we get is a first normal form database. And what we've got is a table that's in a report format that's stored in a table. So you can obviously see we have a project number up here, project name up here, employee number, employee name, job class, charges per hour, number of hours. Kind of looks like that. Employee number, project name. They took the labels on the reports. In fact, I'm sure, not every one of you, but I'm sure there are people out there that still do this because they don't know about how to create a database. They just, you know, and it looks like Excel. They just start putting this stuff in. And we see we have some names listed, and we've got some job class. We've got a little redundancy going on here, and numbers there. That's first normal form. So the structure doesn't handle the data very well. That's hard to query. So first normal form databases, by default, you can't use an SQL query language on them. What would you query on? You'd get, well, you can get project number. You wouldn't get all the data out of the database because you can't put it all together. You only have one table anyway, but you can't put it all together. It's all in one table. What they would do, instead of querying the language, looks like the same report, just print it out. They bring up Access and print out the screen, do a print screen. Oh, look at that. Here's our database. Yeah. Okay, the table appears to work. The report is generated with ease. You just print it out. You got the data right there. In fact, if you use Microsoft Access, you got it in the order that you put it in, which is another mistake that people in first normal form don't think about, is that they assume there's an order to the data when there's no order to the data that goes into that table. Unfortunately, the report may yield different results depending upon what data anomalies have occurred. Depending if you're going to use this as a data report, and you have to manually edit it. So the conversion to first normal form, what we've got are repeating groups. You're going to say, well, who would do this? People do this, actually. So, repeating group, so it derives its name, the repeating group concept, or the terminology, derives its name from the fact that a group of multiple related entities can exist for any single keyed attribute occurrence. So the repeating groups are and here we got groups of job classes. Well, we've got groups of, there we go. All these people are in this project number with this project name. All these people here are over here. They're all kind of grouped together. And, well, we got the project separated up. That's good. So. Alright, so I'm not going to waste too much time explaining something that shouldn't really even be explained because it shouldn't really have been used. But consider the concept of that. And then a relational table must not contain any repeating groups. So first normal form, the concept, and what we're going to do here is going to take and show you each one of the problems we're eliminating. Because when we put something into first normal form, we're removing the repeating groups, as an example. So normalizing the table will reduce the data redundancies in terms of the repeating groups. So what we're looking at is a three-step process to put it into third normal form. So number one, first step is to eliminate the repeating groups. Because we can't just take, and what ends up happening is you follow through this kind of thing when you get a database that you didn't build. Because if you built the database, it would be in third normal form. Hopefully. Or it's going to be fairly close. So you're building something that somebody else created. So you're going to try and first you're going to put it in first normal form, then you're going to put it in second, then you're going to put it in third. So step number one, to put it in first, you got to get rid of the repeating groups. So you present the data in a tabular format where each cell has a single value and there are no repeating groups. You eliminate the repeating groups by eliminating the nulls as well, null values, making sure that each repeating group attribute contains an appropriate data value. All right, so here we've got our repeating groups removed. You can zoom in a little bit so you can kind of see. Now we have no empty spaces. In this previous one we had empty null values, missing information. We've normalized it now to first normal form, believe it or not. And you see databases like this all the time. I see databases like this all the time. And you're looking at it still has problems. Don't worry about it. It's not done yet. But now we have a data value for each one of our cells. So step number two, we're going to identify the primary key, hopefully. Primary key must be a uniquely identifiable attribute. New key must be composed if there is no key. After we identify the primary key, then we've got to look at all the dependencies. So dependency can be depicted with the help of hopefully a diagram, a dependency diagram, entity relationship diagram. This is how I get people that take a database that they've already created and they try to make a diagram out of it. Harder than taking a business description and then creating the diagram out of that. Because the table design that you've come up with, you're already assuming a design without actually looking at it. So you actually have to kind of put and go backwards and create the diagram, depict all the dependencies found within the given table structure. Helpful in getting a bird's eye view of the relationships between the table. Because this is everything. We want to pull stuff out. What we want to do is take this table that we've created and reduce it down into more tables. Pull out some of this stuff. Find out primary key information and stuff like that. So it makes use makes it, I don't know, I can't even read that, much less likely than important dependencies will be overlooked. Okay, whatever. All right, so let's take a look at the dependencies. And this is kind of an interesting way of showing you why we have dependency diagrams versus entity relationship diagrams. And they are actually two separate concepts. The ERDs are showing the relationships, and we've got it defined. And we can actually take that from a problem description and easily create an entity relationship diagram. When we don't have the problem description anymore, when we just have the data, then we have to look at the data and see what is dependent, how the data is dependent upon itself. When we do that, here's our first look at the dependency diagram. Because we have one table, we have one structure. What we're looking at in terms of the first normal form is these partial and transient dependencies, which is what we're identifying. And you're already kind of familiar probably with most of this stuff, but the terminology is probably new to you. When we have a project number and a project name, and then we also have an employee number, we have which is related, because each one of the project numbers has a project name associated with it, which is a partial dependency on the relationship with an employee number, because not all employee numbers match the project number and project name. Oops, I got it backwards. Only part of them do. There's not a full 100% relationship between the two of them, which gives us our redundant data, because we can have project 1 and the project name with employee. Project 1, project name, employee number 2. Project 1, employee number 3. bad design because we have partial dependency looking at that. We also have partial dependency between going this way, the number of hours charged, the job class, the employee name, and the employee number. Because what we could have is different job classes associated with, the employee name and the employee number are probably going to be consistent, perhaps. We have transient relationships, dependencies with job class and charge per hour. We get the job class from job per hour and vice versa, and we're depending upon the job class to give us the charge per hour with an assumption that it's not going to change, that each one of the job classes has the same job per hour. So we're stuck, actually. We're very constricted in terms of the way we're representing that. And if you don't get it from here, you're going to get it. If you don't understand what I'm talking about in terms of the dependencies, we're going to see it when we translate out the table. You'll see why something that's partial should be turned into a full, vice versa. So the first normal form, the tabular format, we saw it already. All key attributes are defined. No repeating groups in the tables. All of the attributes are dependent on a primary key. Don't really have that yet in our format. And all of the relational tables satisfy first normal form requirements, meaning that they meet that criteria. Some of the tables contain partial dependencies. It's okay for a first normal form. And dependencies based on only part of the primary key and not the whole primary key. Sometimes used for performance reasons, but should be used with caution and still subject to data redundancies. We have a lot of data redundancy actually in this particular example. So now let's take this thing here, this really bad design with partial dependencies and stuff of that nature, and turn it into second normal form. So the conversion into the second normal form fixes the design to improve it, converts the database into it. 2 steps. First step, identify the key components. Now we're going to actually kind of split the tables off a little bit, because we can pull some of the data out and key it in instead of having the redundancy in the table. And then we can create a full dependency instead of a partial in some cases. So we can write each one of the key components on a separate line and then write the original composite key on the last line. I'll show you an example of that. Each component will become the key in the new table. And then we're going to identify the dependent attributes and move them into the appropriate table. So determine the attributes, and at this point most anomalies have been eliminated because we might have some things that should be lined up but they're not lined up. Okay, so here's our, remember the last one we looked at was a flat line, meaning it was all one table. And everything was either partially or full dependent. There was absolutely no way of figuring out how things were actually linked together. Oops. Here we have a second normal form example where now we have project number and project name is now into a separate table called project. And we've pulled out, we still have the same set of data, we can actually still put it all by flat. We can still make it into a line. We haven't added or changed anything yet. Employee number and employee name is now with the job class and the hours charged per hour as employee. We still have this transient relationship going on because we still haven't defined job classes yet, or how much the job classes work. We might actually have some hours that are different for the same job classes. We have no guarantee that we have that relationship going on. And then we also have an assignment table where we have an employee number, a project number, and then the number of hours. And you're wondering, why in the world do we have to go through this route? Well, it's because we didn't start with an entity relationship diagram. Otherwise, we would have had this, essentially. That's why we're doing it this method. All right, so that would be the second normal form consideration. Still not there yet. We still have problems. That's actually not perfect. We still have problems with that. So the table is in second normal form if it is also in first normal form and it includes no partial dependencies. We've taken away the partial dependencies, and I'll show you that in a second. And no attribute is dependent on only a portion of the primary key. It's 100%. It's 100% reliant on that. So to turn that into third normal form, we have to get rid of the data anomalies. So the data anomalies created are easily eliminated by completing this in 3 steps. Step number 1, I identify the new determinants. We'll see an example of that. It's going to make more sense. For each one of the so what we're doing, in order to get rid of in order to turn that one, we're actually getting rid of this transitive dependency. We have to make a new table out of job class and specify job class with hours. So we can actually just put job class in here, and we already know the hours. And the hours are fixed. They're not going to be different for each one of the job classes that are in there. So in terms of the determinant, so for every transitive relationship or dependency, you want to write its determinant as a primary key of a new table. So it would probably be job class. So the determinant is any attribute whose value determines other values within the table, which is what meant by determinant. So job class is going to determine how many hours that person gets paid. And then identify the dependent attributes that are associated with that. And so identify the attributes dependent on each one of the determinant. Identify in step 1, identify the dependencies, name the table to reflect the contents of the function. And then the last part of it, we'll see it broken out, so you can point out what it is I'm talking about here. Remove the dependent attributes from the transient dependency. So take everything that's associated with job class out of that table, put it over into its right table. So what you're doing is you're cutting it off again, separating it out. And when you do that, you eliminate all the dependent attributes and from each one of the tables. Draw a dependency diagram to show all of the tables defined. Yeah, you actually have to redraw the diagram to actually show how it works. When you do that, you can actually verify the design is what you're doing. So, because you didn't draw it first, obviously, otherwise you wouldn't have had this design to begin with. And then check the new tables, modify the tables in step 3. Make sure the determinants does not contain inappropriate dependencies or inappropriate characteristics. So here we go. We got our third normal form conversion results. So I'm going to make this a little bigger. There we go. So we still have this table for project. We got the project number, project name. We got employees. This is the new table here. We took job class out, and we made it into a charge per hour that's associated with job class. We do that, then we can have, in fact, you see this all the time in terms of, let's say, the employee table. You see this when you have employees listed, and sometimes you'll have job class, but then sometimes you'll have, like hours of, term or how long that person's been at the company, or employee number, social security number. You see things that are like multiple primary keys or something like that nature. That's actually still in third normal form, as long as you don't have any transient dependencies. Transient one is in which every charged hour we've eliminated, because every charged hour for each job class has to be consistent. So all we do is we say job class, we get the hours, the charge per hour, without having to without having it being different for each job class, or differently displayed in the table for each job class. And then down the bottom we have our assigned table, in which we have employee number, project number, and the assigned hours. So that looks good, huh? Third normal form. We can actually improve that design. So when you take a look at that, it looks pretty good, actually. So third normal form is a third normal form if it's in second normal form and it contains no transitive dependencies. Once we've gotten rid of those, now we're in third normal form. So we can improve it here. Table structures are cleaned up to eliminate the troublesome impartial and transitive dependencies. Normalization cannot by itself be relied upon for good database design. It's probably better not to use this approach, because this is only used when you run into a situation where you already have a database table. Then you run through steps for step 1 for normal form, first normal form, bring it into second, bring it into third. You can't actually take it from first to third automatically, because you actually have to analyze each one of those different characteristics step by step in order to actually come out with a good design from it. Otherwise you keep going around in circles. Change this, oh no, let's change that, change this. It becomes a matter of unorganized spaghetti design. So it's valuable because it helps eliminate data redundancy, helps keep. In fact, third normal form is not bad because you don't have data redundancies and you don't have inconsistencies, and all of the data have primary key associated with them in each one of the tables, so you can identify the data. So in terms of improving the design, you can follow changes. The following changes were made to that particular design. Actually, I kind of just sped out most of them, but I think I missed a couple. We assigned primary keys. Naming convention, I didn't talk about that. We actually set naming conventions for each one of the... I'm sorry?
Yeah.
Oh, okay. For each one of the... a little distracting. For each one of the tables, we name them appropriately. So we have job, project, employee. Attribute, automacy, well, we made sure that we are all storing the same data types and same pieces of information for each one of the employees. We added some attributes, like the job hours charged per job. Added relationships, redefined primary keys, maintained historical accuracy, and also used derived attributes in terms of that. So here's the completed database design in terms of our original example, where we've got the project at the top, and the project itself is going to have an example of the data that's stored in this particular table, project numbers, project name, employee number. And then we have the job, let's say the job table where you have the job code, job description, job charge per hour, rate per hour. So we have the attendance roster going on. I don't know who's the TA for this one. She's no, I don't know. Lost the TA. Out there somewhere. Oh, sending roster around. I mean, attendance list. Yeah. I'm assuming it's going around. So. Oh, now it's going around. Good. Send it out. Yeah. Most people are here by now. All right, so here's the another example of how the tables work together, where we've got, kind of hard to see, it's actually because the slide itself is kind of skewed, where we have the other table for the assignment and the other table for the employees. So we can kind of, the slide is almost impossible to read, probably from where you're sitting as well, but basically the slide's basically showing you how the data examples would be created. So limitations on system assigned keys, because what ends up happening now is we have, in fact, Microsoft Access is really good at this. They give you an index, but it's not really an index on the table. It's an index value. So it's a system-designed approach to put like 1, 2, 3 employee number or something like that to create an artificial index/key. So system-assigned primary keys may not actually prevent confusing entries, because it's really hard to tell what's number 101. Yeah. Who is employee 101? We have no idea. But if we had your social security number, we might be able to look them up somewhere else or something of that nature. So data entries in the table 5.2 are inappropriately because they are duplicating existing records. That was the original spreadsheet report that we were looking at, had duplicate records. Yet there had been no violation of either the entity integrity or the referential integrity as well. So we could have had employees with same in numbers. We could have had the same job titles, different hours. We didn't actually look at in terms of the jobs themselves. So duplicate entries here. Here's an example. Because we thought we had a good table actually. Well, their normal form is pretty good. But here's some interesting things that might happen. Duplicate entries in the job table. So we have the job code, no problem. But what we end up with is a job code 511 and job code 512, both programmers. Fortunately, they're both making the same amount. They're making different amounts. It would depend upon which job code you assign for the same description. So we can improve the database even further by getting rid of this type of an anomaly where we've got duplication that doesn't affect the keys, doesn't affect the referential integrity of the table. Same thing happens actually in a situation where we have tables that have employee names that are identical, and we have the same employee in with 2 different IDs because they're working 2 different jobs. So as an example, if we had a TA and we also had a student table, and the TA table had the same student listed in there, but they had a different code associated with them because they're a TA, and they're also a student, so they actually show up twice in the system, even though there's really just one person, because they can have 2 IDs that are associated with. You get this actually. You see this a lot when you order products from customer. When you're a customer and you order products from a company, and they bring up multiple customer IDs for you, and you say, "Oh, well, you bought one of our DSL packages." Oh yeah. Oh wait a minute. Here you are again. Oh, you bought a computer from us. Oh yeah, a different department. You were in the computer department, and then you were in the services department. But So anyway, that's actually a problem. It's a problem with the system. So this is what this BCNF format, which goes above and beyond. This is like a traditional style way of creating normal forms. Voice cod normal. Oh, I said it right. I have a problem pronouncing that guy's name. This is the name of the researcher who came up with this concept. So every determinant in the table is a candidate key and has the same characteristics as the primary key, but for some reason not chosen to be the primary key. This is where you would have, and what we're going to do is kind of go through, well, what would be in BCNF but would still be in third normal form, or would it be in third normal form and not be in BCNF? What you want is both, but you may not get both, depending upon the nature of how your data is stored. If you've got a social security number and a student ID, you're not in BCNF because you got two pieces of information. You might be in third normal form, no problem, but you got two pieces of information that could be a primary key. What happens with that is it creates two different search criteria, two different ways of running a query, because half of you are probably thinking, what does it really matter? It's taking up space. Well, but that's not really the issue. The issue is you can, select social security number from this table and do a query and do a calculation, and that works just fine. Or you can do a select student ID from this table and think that you're actually going to come out with the same result, but you could actually come out with two separate numbers, two separate counts, two separate numbers, depending upon those data anomalies that I was talking about. Let's say if a TA was in there twice, had two student IDs, but only had one social security number, she'd count twice, or he'd count twice on the number. We'd get a bad number that came out in terms of how many. If we were just doing a count, we'd have twice as many students if we had each student was a TA than if we just did a count on the social security numbers, which causes anomalies in the SQL results. So BCNF format makes your SQL queries more reliable. Third normal form makes your data storage more reliable, if you want to think of it that way. So anyway, so if the table contains only one candidate key, the third normal form and the BCNF are equivalent. Your table's in the same format. BCNF can be violated only if the table contains more than one candidate key, more than one candidate key. And there's a little bit more to it. Most designers consider the BCNF as a special case of third normal form. So the table is in third normal form. If it's in second normal form and has no transient dependencies, as we've seen, so the table can be in third normal form and not be in BCNF. If the transitive dependencies exist when one non-prime attribute is dependent on another non-prime attribute. So going back, if we have employee with a name and we put, well, we wouldn't have an employee name anyway. If you had employee social security number or employee student ID or whatever, I don't know, an ID and a social security number, you wouldn't put a name in there. If you put a name in there, you're not you're going under this category, because the name, maybe you have in their name address, which ends up with repeating information. If you put the name in there, what ends up happening is when you update the employee table, let's say she gets married and changes her name, it's not changed over here in this table. It causes anomalies. It causes inconsistency in transient relationships, dependencies between the tables, right? Within the table itself, actually. And this is for non-prime attributes, actually. Your prime attributes are already going to be unique because you're not going to have that problem, actually, because they're prime candidates. A non-key attribute is a determinant of the key attribute. That would also be an issue. If you had employees that had a column attribute that said TA or not TA, okay, then you have to search on that TA category to see, does it say TA or does it say not TA, in order to determine if that employee is a TA or not, which the ID for that particular person should tell you if it's a TA or not. So the primary key should tell you who the person is without having to depend upon another piece of information that's in the table. That's actually part of an okay for a third normal form. We have those in third normal form. We have all these problems in third normal form. We don't have them if we're BCNF. So a table that is in third normal form but not in BCNF, here's the table here. We have transient relationship actually between, it's harder to look at it with the ABCDs, I know. The thing about it, we have non-key attributes that are dependent upon, key attributes that are dependent upon non-key attributes, perhaps. And then we also have information that doesn't belong that can be used as a key. So you could put, employee last name, employee number, employee social security number. That might actually be existing. So if we decompose and we put this table into a BCNF, we're breaking it out even further. So yeah, I know the solution to the problem is take the table and break it out. Break it out, break it out. So what the moral of the story is not count the number of tables. If you got a lot of tables, you got a good design. Although, to get a good design, you have to have more than one table. So you can't just use that logic. So if you decompose it, here we have A, B, C, D all in one table. And we have these interrelationships that are existing. Here we've taken third normal form, but not, this is what we started with. We moved out the partial dependency, we split it out. So now we have third normal form and BCNF. And third normal form and BCNF. We have two tables that follow both. So we have A, C, D, and CB. So we can link up the C's here and get the information that we're looking for. So we have essentially pulled the employee's name or anything associated with the employee out of that table, and we've linked it with the primary key of that table, which would be C, this attribute C here. And we took everything else that didn't belong to C, that's associated with C, we put it out into a separate table. So we got rid of the partial dependencies. Otherwise, we could have essentially the case in which we have an employee in there that has the different name in this table than they have in this table over here. So we get, and it's partially dependent upon where you find the name as to what name you're going to get in terms of the printout of that information or the query of that information. All right, now what do we have? Let's take a look at our table. Here's the sample data for the BCNF conversion. Put this, instead of looking at the ABCs, might probably make more sense if you look at it this way. So we have student ID, staff ID, class code, and enrollment grade, where we have this student 125 is assigned to this staff 25. We also have 144 assigned to 25. The class codes are all different, and well, the grades don't really matter. But they matter to you, they don't matter to me. All right, so we have the class codes that's associated with it. And so if we take this, by the way, is in third normal form. And most of you probably look at this and go, looks fine to me. But we can arbitrarily put in any class code we want. We can arbitrarily put in any staff ID we want. But that staff ID and the student ID is not really a problem. It's the class code that might be different depending upon how we have it set up. So another BNC decomposition, if we take this here, student ID, staff ID, class code, and enrollment data is how we started out with, which is in third normal form, but it is not in BCNF, but it is in third normal form. Most people look at that and go, oh, there's nothing wrong with that. Looks pretty good. It's probably because I'm going through it too fast. If I slowed it down a little bit and stare at it for a while, I still don't see anything wrong with it. Wouldn't change your opinion, probably. Panel B, now we are in BCNF because we took out the class code and we made it so that we only have certain class codes that can be entered in here. And all the class codes are going to have the same staff ID associated with it. In this table here, we can have teachers that didn't teach the class. We can have mismatches between the staff ID and the class code, which is okay. It's third normal form, but it's not BCNF because we can have, there's the possibility, and this kind of shows you that transient relationship again. And there's a possibility of there being the wrong class code assigned to the wrong staff ID, which would make the data useless because it's almost like you're taking a class with a teacher that doesn't exist and getting a grade for it. And then when we query the table for the class, we're not going to find, you're not going to be in any of the search results. It's not going to show up on your transcript. And who knows, we probably have that problem here. I don't know. Ooh, okay, I'll stop with that. This is not bash the EMS night. Although, let me tell you how I really feel about that database. All right. So do we see the difference between third normal form and BCNF? I'm going to ask you this on the final exam, actually. Somebody, because someone's going to, she's not here. Somebody, maybe she is here, I just don't see her right now. She moved. Somebody asked me, because they're already thinking about the final. The final is actually about, what, a month away or so? It's about a month away. People went, what's going to be on the final exam? I'll take a few moments here now that I mentioned it. Multiple choice, fill in the blank, closed book, closed notes, in class. But I'm going to ask you questions that are theory, concept-based. One of them I know I'm going to ask you at least a question on normal forms. Because I want to know, did you actually understand what is meant by... I'm not going to ask you what's third, first, second, third. I'm not going to do that. I'm going to say, well, what's the difference between third normal form and BCNF? Describe the difference between the two of them. And you can draw a table if you want. You can draw... So knowing the concepts, or or even a question like multiple choice that says, can you have something that's in third normal form that's not in BCNF? Is it required? Is it automatically defaulted to to this? So if you don't know the terminology, I'm not going to ask you what is BCNF. I can't even pronounce it myself. Boyd Collar something or other. Boyce. This is the guy's name. I know he's probably rolling over right now, going. All right, but that's a sample kind of thing, like why do we want to have normal forms? Why do we create entity relationship diagrams? I don't know. Because they're fun? No. What happens if we don't create a dependent? What are some of the things that could happen if we don't use a design methodology like an entity relationship model? Well, there's more than that out there. There's tons of different models out there. That's the one I like. I shouldn't say tons. There's a handful. There's one or two. Not too many to choose from, actually, and they're all variations of entity relationship. But anyway, not my point. My point is why do we want to do that? Well, because then we're going to have partial dependencies. We're going to have transient dependencies. We're going to have situations in which we have repetitive, duplicated data that might be inconsistent. We're going to have data that we can't get at, as we've seen in here, because there's no way of querying on it. We're going to have inconsistencies in our query results because we have multiple keys, perhaps, instead of just one key that's identifying each one of them. And we're going to have entities that are really relationships. So we're going to be storing information in tables that don't actually belong in a table. So usually, after I show the normal forms, usually students kind of go, oh, that's why the entity relationship diagram works. Because it separates everything out and puts everything into logical categories and reduces all of the issues. But you don't always get that. Half the time you walk into a company and they already have a database created. And you look at the database going, oh wow, this is a mess. Can we get it into third normal form at least? And then we work on the BCNF if we want to. So here's normalization and database design in terms of the summary part. Naturalization should be part of the design process. So if you're following an ERD kind of concept, you're doing it for normalization. So did I say nationalization? Normalization. I know, I caught myself. I'm like, nationalize. These are international databases. At International Technology Databases. ITD. All right, so make sure that the proposed entities meet the required normal form before the table structures are actually created. Because here's what ends up happening. You start using those DDL commands to drop or to add columns to tables, remove columns from tables, move this over to here. A lot of work. It's almost like you built a house and you decided to restructure it. You got to take everything down and you got to build new walls. It's just more work than if you just started with a good design. So many real-world databases have been improperly designed and burdened with anomalies and improper modifications during the course of time. It's just like software engineering, just like development. The more you work on this database, the more you add to it, the worse it gets. However, if you don't touch the structure of the tables and you just add new tables to it, you minimize the damage. Where most people end up with problems is they start adding columns to tables. And then you have half of the data has the value. The other half of the data, after you added the column, It doesn't have, this first part doesn't have it, the second part has it. Now you have some, you go back to nothing, you go back to before first normal if you saw that spreadsheet where half the columns were empty. You take the whole table back to below first. It's not even in first anymore. So you can deteriorate the normalization of the table by making structural changes to it after the original design was created. You might be asked to redesign and modify existing tables. ER diagramming, this is why we're using it, provides the big picture or the macro view of the organizational data requirements and the operations, how you're going to use the data, because it shows you not only how you're going to use it, what you need to store, what data has a relationship with the other data, and it gives you your key structures. And it allows you actually to kind of, even if you don't even do the ERD, you just do the dependency diagram, this is the shortcut ERD, it allows you to kind of come up with a better design up front. Created through an iterative process, theoretically identifying relevant entities, attributes, their relationships, and then using the results to identify additional entities and attributes that might exist as you go through and verify the design. So, I know it was kind of quick, but that was database normalization. And it is actually lecture 6B, if you're interested in knowing that. Because some people will want to take a look at it, and they'll go, well, you know, let me see that list a little bit better. Because if you wanted to, you could actually write down the list. There's different characteristics that fall into first, second, third, and I just stand here and drill it into you. It's in the slide set. So. And I forgot to download 7, but we still have a little time left. So let me find. Actually, did we skip 5? I believe I skipped 5 because 5 had to do with. Did I skip 6A? Some people who've been here before. I went over 6B. I think I skipped 6A is what I did. 6A, and let me just run through 6A. Actually, it's going to be a repeat. It goes through the relational database concept, but we already know that, hopefully. Let me take a look at 6A real quick, actually. Refresh my memory. I think I did skip it. I went out of order, and then as soon as I went out of order, all of a sudden I kind of lost track. I knew we were on the 6s. Yeah, 6A, I don't think we've done 6A. We did 6A probably earlier on. Tables, let's see. Let me just make sure that there's nothing in here. Controlling redundancy, characteristics, keys. No, we did this. This looks familiar. All right, okay. Consensus says we did it. Then I will take your word. Let's take a look at 7A. Last week we did the PLSQL, right? So that was 5, I think, wasn't it? We didn't do number 7A. It's kind of intense. We have choices. Let's see. Hold on one second. Let me just take a quick look here. I know I probably should have done this before, but I was distracted. Blame it on the students. I was distracted during my break before this class. You guys getting You guys are getting restless too. Storage. Storage settings and concepts. Hold on one second. Let me just make sure. We might be ahead of schedule, actually. I just want to make sure we covered 5A and 5B as well. Yep, 5A was SQL. We did that one. We did that one. Nope. Nope, we're on track. We're actually kind of ahead, I guess. How did we end up ahead of schedule? Someone remind me that this is 7A. Because I'm going to start it, but I'm not going to be able to finish it. All right, so we've actually covered most of, if not all, of the database Oracle kind of components in terms of the SQL engine, SQL Plus, PLSQL, entity relationship diagramming, normalization, a couple of other topics, relational database concepts. We've covered most of the foundational stuff in terms of the design, the components, the structure, and the administration. What we haven't looked at yet is the Java interface and all of the database connectivity in terms of the packages and the support that you might be interested in, especially if you're taking the object-oriented design course or any type of networking class that works with databases. Because what we've actually seen is the connectivity in terms of SQL. And as I mentioned before, I've been alluding to actually kind of the concept of using a database on the internet and having a master internet account that has very low security, hopefully, that sends back and forth a login that basically all it does is send a query. You send an SQL statement, run the query, receive the results, set back, parse it, use it. And in terms of Oracle, it runs just like most other, in fact, if anything, because it's a client-server database, and it has a lot of good security associated with it, it lends itself quite well for connectivity. And unless you've got a ton of bucks and you're working for a company who loves to spend on Oracle products, you're probably not going to be using Oracle interfaces, Oracle-related products to build your front end. So what this lecture actually kind of goes about is this concept of building the application and interfacing through the database, through some sort of a DBMS driver, some sort of an interface. And what this is kind of surveys through a lot of the different common techniques for building application front ends. Because what we've covered essentially to this point is everything that's associated with it. Now it's time to look at reports, which is coming up. I believe the reports comes after this. Form generating, connecting to the database, which is this lecture here. And then some of the Oracle features in terms of, and they've all changed, actually. So it makes absolutely no sense to go through each one of the Oracle interfaces features because first of all, hardly anyone uses them. They all use third-party tools. But every new version of Oracle has a new set of everything. So that's actually the last part in which, like the last 2 weeks of the class in which we'll go over backing up, restoring, creating table spaces, and some of the rudimentary kind of Oracle interfaces. But in terms of what we're looking at, in terms of the connectivity, I want to go over the motivation, the architectural, the 7 kind of steps to connect, and a sample program, the concept of the metadata, and being able to use the metadata in terms of the Oracle interface. And Oracle actually makes JDBC a cinch because the driver is very feature-rich, and the same technique can actually be used with MySQL and some of the other databases out there. So it's not exactly 100% Oracle specific. They're not going to support it to the same extent. The drivers aren't quite as good, but the functionality is still there. So, and you'll be surprised how extremely easy it is to use the JDBC and some of the other interfaces. So the motivation is most popular form of database systems is a relational system. We're looking at the SQL interface. Once you've learned the SQL interface, you're going to use it. And applications need to query the database, which is essentially all they're doing. And I can't tell you how many times, I mean, every application out there connects to a database these days. You can't actually find one that doesn't. What we have, though, is an application that can actually kind of connect to different databases through different database objects and provide a connectivity, which kind of this picture kind of displays in terms of the multi-level database access. Using tools like JDBC, actually in a Java interface, allows you to keep track of different connections and manage the network and the connectivity end of it with very little effort. I say. This is why I kind of like to introduce this because it shows you how easy it is actually to connect. So standard access to a database, what we have here is the application, the driver manager, and driver 1, driver 2, driver 3. Different drivers going to different database management systems that are actually connecting to the database. So your interface through the application level is through the drivers. So it depends on the driver support, seriously, as to how good your connection is going to be and how much functionality might exist through that. Drivers are all open source. You don't pay for drivers. In fact, the manufacturer of the database doesn't even, well, some of them do. Some of them actually, they want to support the driver because they want you to use it. But the drivers themselves are pretty standardized, and they're I wouldn't call them open source, but they're close to it. There are some open source generic drivers, but they're not quite as reliable. You might be wondering, how would reliability be an issue? Well, you want the driver to work. you want it to function properly. You also want it to give you the correct results and parse the information correctly, and hopefully give you metadata about the query results that you've gotten, give you the ability to store procedures maybe, give you the ability to cache results, provide some good management via the connection itself, error checking and stuff. And that's where you kind of get the difference between an open source driver and a good one. Not to say that open source isn't good, but between one that's really had a lot of development effort by the manufacturers and ones that are kind of slapped together by third-party people. Oracle, for one, is really good. They've actually paid a lot of attention to their driver development. They don't actually make it, another company makes it, but they've provided the support, so it's fairly reliable. I mean, I would say 100%, but more so than any other database set of JDBC drivers out there, actually. So, which makes this a very strong selling item, or a strong selling platform. Here's the ODBC connection through the architecture in terms of what we're looking at. And ODBC, JDBC is Java-oriented. This is object database connectivity, which is what you're going to get in a Windows system, what you're going to get on an application that runs on a standalone computer, or one that's networked. Depends on the environment. They're both doing the same thing. So we have application, we have a class 1, class 2, or executable 1, executable 2 out here. We have our driver manager, and then we have our data sources. If you've ever worked with Visual Basic, that's where you get the ODBC connection. Old Windows 95, 98, even XP I think still supports it. I think this concept was upgraded in Windows 7, but I haven't had any chance to experiment with it yet. Not bad for standalone, but kind of slow. Because here's the other problem you get. You get very slow connectivity activity through ODBC. If you can cache some of the information, have the driver working with the operating system more transparently, have the driver work with the database more transparently, you get essentially faster interface, faster communication, faster transfers. Because what you don't want is to build an application, especially a web application, it's going to sit there and wait for the database. And what it's really doing is waiting for the driver, because the driver is stuck trying to do something and it can't communicate well, or there's an issue with it. So in terms of the open database connectivity is what we get. Here's a little bit of background information on it. Some of you may or may not have ever seen this on a Windows system. It also works on a Mac system. It works on any host operating system. It's kind of a generic platform in which we've got an interface for the application programs to access and process SQL databases in a DBMS-independent manner. So it doesn't really matter which database, theoretically. Some work better than others, I've mentioned. The data source, the database management system, the driver itself, and the driver manager are important to consider. And actually on the bottom here, you're going to control, this is the pre-Windows 7. I believe it still works in, does it still work in 7? Someone ever tried this in 7? Yeah. Okay, so there's Windows 7. I thought they upgraded that process. That works still? So it's backward compatible? Have you ever used, have you used this? Oh, no, I mean the ODBC interface?
In my program, I use
okay, good. Because you know what happens? People go, oh, I've never used it. Why is she even talking about this? All your third-party tools are using this. Common problem, actually, when you install Crystal reports. You know, I think one of the assignments actually has you pick a reporting tool. You actually have database, you actually have Oracle running on your system, and you can't get to it through the operating system. It's stuck. Because you need an ODBC driver installed. So when you install Crystal reports, you guys have heard of that, right? And it's like one of the most popular reporting software packages out there for databases. Used to be, I should say. But even like PeopleSoft interfaces of any application development environment, Visual Studio, Java, you got to get through a driver. It's going to be JDBC if it's Java oriented. It's going to be ODBC. So it's like, well, this is old and outdated. Nope, still being used. And I'm glad that they kept, because I heard that they were upgrading the support. Because a major problem with Windows and ODBC is it's slow. And it can't handle the data transfer. So you load an ODBC driver, you got your Oracle running, your Oracle system running on your network. You've created a Crystal report for your customer to run. They put in the information that they're trying to get from the database. They press run, and they go to lunch. And they come back, hopefully by the end of their day, the report's there. You can't wait. What if you need it now? What if you need it before you go to lunch? And half of the problem is that connection through that ODBC, and the size of the query, and the parsing of the query results, and the design of the query. You don't have that much control when you're relying upon a Windows product. You're stuck. So that's why people go JDBC, but anyway. All right, so the ODBC interface. What I'm going to do here is I'm going to introduce you to the interfaces, and then I probably will stop halfway in the middle of this, because next time we can actually look at the Java interface to it. And everyone taking the Java OOD class is going to love it, because instantly you can create database applications that will work with the Oracle system. Easily. All right, so it's system independent. The interface itself runs with any database. It requires a driver provided by the database host operating system if you want to manipulate the data. You can manipulate the data through the ODBC interface, however, some of them are kind of restricted. In fact, some of them actually have to work with rights and privileges, because sometimes the connection to the database through the driver has limitations. It's kind of like when you load an applet on a website, it won't let you write. It won't let you write to a file or open up, Actually, it'll let you write, it won't let you read, I don't know. Now, it has file I/O issues. I'm not quite sure what the limitations are. But so do the ODBC interfaces. And what they are specifically depends on the database manufacturer, depends on the driver that you're using. Some actually just allow you to query, you can't do an update. Some allow you, only so many connections simultaneously. So there's some restrictions on the drivers. It's because they have to manage, you're building an interface to manage your connection to this database. So it bridges the differences between the ODBC independent interface and the dependent interface of the driver. Because at this point, what we've been talking about is the dependent interface, the SQL Plus window, or the Oracle tools that we actually haven't looked at much. Maybe we'll bring them up next week, or I'll do a video on them that show you like the web interface to it. It's nothing. It's just it's through an Apache server to be able to actually kind of go in and run graphical version of the SQL Plus window. Oracle itself does not come with a reports program, does not come with a form generator, does not come with any of this stuff, actually. So if you want to write an application, you either have to purchase their products. They even have it. They have Oracle Developer. They can actually write it. But if you're going to spend that much time learning Oracle Developer, you're going to probably learn Java instead in half the amount of time and be able to use that on other projects and other applications and not spend any money on it. So it's kind of a tough call on that one. So here's an example. We have an application. We have the ODBC standard API. It runs in between the application driver. There's a driver manager. And we have the Oracle, the DB2, the SQL. Connects to all of the databases. So it's a standalone in-between thing. Here's the part I really wanted to introduce to you because this is used a lot, actually. The support through Java and the connectivity. So when an application is written in Java, the access to it is through JDBC API, Java Database Connectivity. It is specified as an interface. So you actually build a driver actually don't build it, you make an instance of the driver object, and you call methods of the driver object to connect, to disconnect, to do it. And you're basically doing Java programming using a third-party API tool for the JDBC. And I'll run through the steps for you and find, in fact, if I think about it, I'll make sure I have everything installed and I'll demo it next week for you. So you can actually kind of see how easy it really is. And then at that point I can also compare that with the tools that you're given. Your Oracle Express has nothing. So there's really nothing to show you. But there are a few little things. Like, the SQL plus one we've seen already, but there's a couple of other backup, there's a minimal backup recovery tool, network monitor tool, little bits of utilities for configuration, but they're not giving you very much, is what I'm saying. In fact, that's what you get with the real version too, which is why people go ODBC route, JDBC route, and build applications in any programming language that you want, any environment. You could just connect to it. So let's see. So we have different implementations. It provides a convenient way to realize many different drivers that exist. And so you can manage the interface through the interface manager, through an API. And here's where it fits in. It fits in, replaces the ODBC. So, and it's not platform dependent, because Java is not platform dependent, it's multi-platform compatible. In fact, mix in JDBC with the Enterprise Edition, which is what you get if you take that client server in the internet class. You get JDBC with RMI, with Java Beans, with all of the different enterprise computing components. You just slap it all together and you get a really, really strong free development environment where you can develop all sorts of distributed client-server kind of programs using databases and all sorts of different network utilities. So it fits into the package, fits into the model quite easily, which is why a lot of people go the Java route, actually. A little bit easier than going the Visual Studio.NET route. The .NET route isn't going to give you the same type of support with the same ease and freedom of development. All you .NET people are probably going to, yes it does. It's different. I don't personally think it's as easy though, but it is. The capability is there. You can connect. You can't use an ODBC. You can't use a JDBC type of interface to it, but you can connect. Functionality is there. So here, instead of having this driver manager with all the databases, we actually have a simple application interface through an API, through an Oracle driver, through the database. We also have this support. This is why people go the Java route, which I don't think you actually have the .NET route, but don't quote me on that. The Java support for the embedded SQL. So you can actually put the statements in your Java code, send them to a connection run a connection method with it, and keep a text string in your program of all of the different SQL statements and stuff like that. So embedded SQL in Java, SQLJ is one of the versions of it where we can actually, we can actually write the code in the Java. Provides a standardized way for Java programs to interact with multiple APIs, multiple databases, but at a high level than the existing JDBC or interfaces themselves. It's an add-on. You don't actually have to use that. You can just use JDBC with regular old Java. Create a text string, and there's your SQL command, and send it to the driver through a connect, and we'll see that. Actually, I'll demo it for you on Thursday, or excuse me, on next Monday. I'm like, what day of the week is this? All right, so embedded SQL allows connecting to the database by including SQL code right in the program. So the embedded SQL processor converts the SQL statements, and again, you're using another API to convert the statements to the Java code. So when you basically make it into the bytecode that's going to be compatible for the JVM. And you don't have to use the Enterprise Edition for this. You can actually use the standard JDK for this. So the java.sql package and the extension, the exception hierarchy that works with that can actually debug your code. Because here's what the problem is. And a lot of you are like, all right, people pay the big bucks for the Oracle tools because it has built-in I/O exception handling, or built-in exception handling, because it's a closer interface to the Java environment. It actually runs a little bit faster because there's no driver in between. And so you could put forms, Oracle report, you could put all these packages together, and if it comes back, it can try again. If the connection fails, it can retry, it can resend, it can fix itself, has built-in error handling and control. Outside of that environment, you have to do it yourself. So the APIs and the tools, like the Java SQL, has minimal, but it does have some error handling, error IO exceptions that are included in the interface. They give you add-on utilities or add-on capabilities that the Oracle, true Oracle product would actually provide you with. So we have the data source and the driver. The data source is the database that's created using any of the common database applications. So the data source is your tables, your database object that you've created. Your system should have a driver for the database that you're running, MySQL server, JDBC servers. These websites actually work. You could go to jdbc.oracle.org still, and it's still up there. It hasn't moved. So the components, do we want to get into that? No, actually this is a good stopping point. We can actually end early today. I must have talked fast today, I don't know. You know, I'm actually going to stop midway through because what I'm going to be, this next part of the lecture goes through the actual components and the connectivity. And I don't have my example with me to show you anyway, so I'd rather wait, load it up in your Eclipse and show it to you next week along with the rest of this lecture. So I'm going to leave about 15 minutes early then. All right, a few administrative details to cover for those people who weren't here for the previous class. Next week, we're meeting at the new location. So we'll be in San Jose next week. Don't come here. Same class start time, different building. I have no idea what room. I don't even know for sure. We're gonna, well, we'll have a room big enough, I hope. But we know what room number? No, we don't know what room number. So maybe they'll put a sign up or something. If you don't have the address of the new building, it's on the website. I think the TAs have also sent out an email message, that have been announcing it. A few side notes for those people who haven't been receiving the emails or haven't been in the loop. You do not send a copy of the CSLO to the TAs anymore. So instead, you upload it directly to the ITU EMS. The TAs are not reviewing the CSLOs anymore. CSLO is due at the very end of the course, which is May 9th or something. Whew. What's the name? And you guys know. I'll ask my students. May 9th? Okay, good. Because May 2nd? May 2nd. I don't know where I got the 9th from. May 2nd. Okay, good. So if you have a problem, and I know I'm repeating information you may have gotten by email, but some people didn't get the emails. So that's why I'm repeating it. If you have a problem uploading assignments into the ITU EMS, don't bug us. Send a message to tech support, TECH support, at itu.edu. Your name, your student ID, your class, a description of your problem. If you don't get any response, you can bug us. And you can bug us anyway. But you'll get faster results if you send it to the technical support people. I think they're in the process of moving everything right now. They might be running a little bit behind. I don't know what's going on with that. And did I forget anything else? Midterm is due. We don't have a midterm for this class. We don't have a midterm for this class. Anything else? Okay, good. We're done. We're done for today. So remind me, this is where we stopped. Yeah. Okay, good.